Okay, so this is the introduction to chapter 18, which is more thermodynamics. So if you recall from Gen Chem 1, you did the enthalpy. Now we're going to kind of shift over, recall enthalpy, and move on and expand it to entropy. Now, if you were not very strong with enthalpy, go back and review it. So when we talk about thermodynamics versus kinetics, remember kinetics is the energy associated and thermodynamics is also energy associated. But when we talk about thermodynamics, we talk about it in terms of reaction progress, where kinetics is the energy needed to immediately kind of get over that hump for reactions to start forming products. So when we look at this, we're going to talk about it in terms of things that are going to be spontaneous or non-spontaneous. And hang on, let me get my pen going. And when we talk about things that are being spontaneous, that means they're just automatically going to go. For example, it can be fast, it can be slow, but if we talk about it in terms of diamonds and graphite, remember diamonds are carbon under pressure, under extreme pressure, where graphite, it's less organized. And again, think about like what we use in our pencils to write with, okay? So when we talk about it, the takeaway here is going to be this right here. Spontaneity is determined by comparing the chemical potential energy of the system before and after the reaction. So what does that really mean? All that means is if something is going to spontaneously occur quickly or slowly will depend on the potential energy. Iron rusting is spontaneous. You know, we can see cars in a junkyard that go from nice paint, you know, and then they'll get a little ding in it and it'll rust pretty quickly with the weather conditions. However, it is not spontaneous to get that rust to turn back into the metal in the paint. That just will not happen. Just like a waterfall flowing upwards is not spontaneous. It's never going to happen. Oh, look, and here's my my example. So we know going from this to this is completely spontaneous. The reverse of this, not spontaneous. Again, will never happen. If a process, this is another takeaway, if a process is spontaneous in one direction, it must be non-spontaneous in the opposite direction. Again, a rusting car, a silver tarnishing. Now, can we clean the silver off and get that tarnish off? Yes, we absolutely can. But that's not a process of taking the tarnish and turning it back into the silver. It's simply cleaning it off. Again, a waterfall flowing upwards as opposed to, you know, over a cliff. So when we have a spontaneous process, we either, you know, generally speaking, we're talking about a release of energy from the system. Remember, we are still back to system, surroundings, and universe. So when we talk about a higher potential energy to a lower potential energy, those are going to be our exothermic reactions. And if we're going from a lower potential energy to a higher potential energy, those are going to be our endothermic. Now, just because something's going from a lower potential energy to a higher potential energy does not mean it cannot be spontaneous. It just means it's more difficult to achieve, and more energy is going to be needed for that to happen. So in Gen Chem 1, we talked about enthalpy, which is our delta H. And now we're going to introduce entropy, which is delta S. And then eventually we'll get to Gibbs free energy and kind of combine all three of them and see their relationships. Now, enthalpy, if you remember, that was based on internal energy and the PV work energy, if you remember Q and W and all that. Where entropy, we're talking about, I don't want to use the word chaos, but really it's a matter of how chaotic is the system. And by chaos, what we mean is, are we going from a very organized thing like a solid to a less organized, more chaotic gaseous phase, for example. So with delta H, if you remember, this is just kind of a review. So go ahead and review these. If it's been a minute or if you weren't very confident in it. We knew and learned that when delta H is negative, it's an exothermic reaction. When it's positive, it's an endothermic reaction. Now, entropy, S, is just simply this. We're back to another K here. It's another constant. In this case, it's the Boltzmann constant, 1.38 times 10 to the minus 23 joules per Kelvin. W is the number of energetically equivalent ways a system can exist, and random systems require less energy than ordered systems. And that should make sense because if they're random, think of just a gas in a container, a sealed container. Those molecules are just going. They just go, and they don't really need much to make them go. In fact, the gaseous state has the highest kinetic energy out of the three states. So, I'm sorry, that's my poochie. So if you remember, delta E of the universe is equal to 0, and it's also equal to delta E of the system added to delta E of the surroundings. Likewise, delta S of the universe, this is our second law of thermodynamics, delta S of the universe is equal to delta S of the system plus delta S of the surroundings. And for a reversible process, this is key here. Delta S of the universe is equal to 0. That means the delta S of the system and the delta S of the surroundings will net out to 0 if it's reversible. If it's irreversible or spontaneous, delta S is going to be greater than 0. So far we have exothermic reactions that are spontaneous, giving us a negative delta H, and then delta S, for it to be irreversible or spontaneous, delta S will have to be positive. Okay? So you can go ahead and look at this in your textbook. It's just a way to kind of describe what's going to happen with the states naturally if you were to remove the stopcock between the two round bottom flasks that are connected with a tube. A couple of things could happen. These gas molecules could just all shift here, like state B. They could stay where they are, like in A, or they could evenly distribute. Most of the time, they're going to be evenly distributed. Don't worry about the macro and micro states. So again, changes in entropy, it's just going to be like every delta we've had before. Delta T is final minus initial. Delta H, final minus initial. Delta S, same thing, final minus initial. Lots of equations in this chapter. And if you look at your TRO constants and equations cheat sheet, if you look on the third column, about a quarter of the way down, that's where you're going to start, where it's the S equals K natural log of W. All of these, rest of these equations, up until delta G naught, no, not delta G naught, the ln of K equals delta H of the reaction over R. Those are going to be the reactions related to this chapter. The rest of those are for the redox and electrolytic cells. So when we have a change in state, that's when we increase or decrease our entropy. So like we said, gas has the highest entropy, and solids have the lowest entropy. So when we're going from a solid to a liquid, we're increasing the chaos, therefore we're increasing entropy. So if we look at this, there's ways to predict the sign of the entropy change. So remember, for it to be irreversible or spontaneous, we're going to have a positive delta S. So in part A, if you go from a gas to a liquid, gas has a higher entropy than liquid, So the entropy is going to be decreasing overall. That's going to give us a negative delta S for this one. Okay, solid carbon dioxide sublimes. If you remember, solid subliming means it's going right from a solid to a gas, bypassing that liquid phase. When we go from a solid to a gas, entropy or chaos is increasing, and that will give us a positive delta S. And then finally, for C, you'll note all of the states are the same. So we can't look at states here. Now what we have to do is look at what are the moles doing. I have a 2 going to a 3. 2 moles of the N2O going to 3 total moles. 2 from the N2, 1 from the O2. So because the number of moles are increasing and they're all the same state, we can also say that's going to be a positive delta S, because an increased number of moles is increasing the entropy or chaos. So one of the ways we can quantify all of this is understanding this relationship where Q of the surroundings is equal to negative Q of the system. But then we can make this relationship between delta S of the surroundings and delta H of the system. So really, really important equation is going to be this one right here, which you're also going to have to remember we can relate it to enthalpy. So let's look here. First, it says calculate the entropy change in the surroundings associated with this reaction occurring at 25 degrees Celsius. Before we do part A, let's just talk about whether or not we think the entropy will be increasing, decreasing, or staying the same. So you'll note in this reaction, it's all gases. So we can't look to the states to see what's happening. What we can do is we can compare the moles now. I got 5, 6 on this side, and I got 3, 4, 7, so 7 on the product side. So because the moles are increasing, we should expect to see a positive delta S. Let's see what we get. Okay, so we're just going to use that last reaction to plug and chug, or the last, equation to plug and chug. And we're using that one because we're not given a Q, but we are given delta H of the reaction. So when you plug and chug, make sure your units are matchy-matchy. And then often the final units needs to be in joules per Kelvin. So once you just take your delta H of the reaction, which was given, and your temperature converted to Kelvin, which was also given, you're simply just plugging and chugging. Do the math, and sure enough, lo and behold, we have a positive delta S of the surroundings, which is what we would have expected to see. Part B is asking us to determine the sign of the entropy change for the system. Well, didn't we just solve for that, Miss Merriweather? No, we did not. Kind of. But we did it first just to see if our answer would be on track. Would it be a reasonable answer? For example, if you had gotten a negative here, that might tip you off that, oof, okay, I've done something wrong, something is not right. So we can say, yep, number of moles on each side, because they're all in the gaseous phase, 6 and 7, we would expect to see a positive delta S of the system and the surroundings. So what does that mean? Determine the sign of the entropy change for the universe. Is this reaction spontaneous? So we just solved for delta S of the system as being positive, and delta S of the universe also as being positive. So the only way to really get delta S of, I'm sorry, I just said universe, I meant to say surroundings. We know these were both positive. So the only sign our delta S of the universe could possibly be is positive. And if it's positive, then the reaction is spontaneous and irreversible. Now, sometimes you'll see a question. Let me see if this one does it. Yes, like here. If you were to go through this one right here, given parameters, you're told delta H of the reaction, you're told a delta S of the reaction, and it's going to ask you at what temperature is the change in entropy for the reaction equal to the change in entropy for the surroundings. That's when you have to set them equal to each other. However, you might see one like this where it says, is this, here's the information, is this a spontaneous reaction, right? And you'd have to go through all of the steps A, B, and C that we just did. Then there might be a part D that says something to the effect of, if it is not spontaneous, at what temperature does it become spontaneous? And that's when you need to set delta S of the universe to 0. And, and then solve for a new temperature. So just because we have low temperatures where delta S of the surroundings is positive and delta S of the system is negative, that doesn't mean that overall it can't be spontaneous. It's going to come to the difference of these two. If this is negative and this is positive, or even over here, if this is negative and this is positive, how much more negativeness or positiveness can we mathematically have a difference between to have high temperatures or low temperatures and still be spontaneous? So if you look at low temperatures, in order for it to be spontaneous, you're going to have a very large positive delta S of the surroundings and a smaller negative delta S of the system. Your perfect example is water freezing. It is absolutely not spontaneous for water to freeze at 50 degrees Celsius. I mean, its freezing point is 0 degrees Celsius. So it should make sense that at higher temperatures, some things are going to be not spontaneous. However, at lower temperatures, things can be spontaneous. So again, water freezing. It is totally spontaneous for water to freeze below 0 degrees Celsius, but completely not spontaneous and won't happen for water to freeze at 50 degrees Celsius, for example. So temperature dependence of delta S of the surroundings is really, really important. So when we talk about entropy change, we talk about the system, it being favorable or unfavorable, meaning is the system, because remember, we can define the system however we want. We have the system, the surroundings, and then the universe, if you remember from Gen Chem 1. So here's our system, and we can define that however we want. Here's our surroundings, and everything else is the universe. Okay, so the example I always give in Gen Chem 1 is if we're defining our own system, we could say something as simple as the test tube is the system, the classroom is the surroundings, and everything else is the universe. Or we could define it and say, okay, our classroom is the system, the building, SciTech, is our surroundings, and the campus is the universe. So we can really define our system and surroundings however we want. But when we're looking for favorable surroundings, we want to give our surroundings or our system, we want to define it in a way that makes the positive entropy change, a favorable or positive entropy change. So now let's get into Gibbs free energy. This is just another tack on. We started off from delta H, okay? We know that when delta H is negative, it is exothermic. And typically we'll see a positive delta S. Now for spontaneity, we'll see a negative delta G. Okay, you can see how the signs are kind of flip-flopping. The opposite is going to be true with a positive delta G. So with endothermic reactions that are spontaneous, we're going to get a positive delta H. We know that's going to be endo. We would expect delta S to be negative and a positive delta G. Now, there are different ways that we can get these. If you look at these kind of summaries, what way can we get delta G to be negative? Under what conditions? What are the favorable conditions? Well, if delta H is negative and delta S is positive. Exothermic, it's more random. That should make sense. For example, going from a liquid to a gas or a solid to a liquid. That should make sense. When delta H is negative and very large, and delta S is negative but small. And the reason for that is this relationship right here. Delta G is equal to delta H minus temperature times delta S. Okay, so if I have a very large negative delta H and a relatively small negative delta S, or a relatively low temperature, mathematically there's not going to be much to bump this, to be bigger. Delta H is positive but small, and delta S is positive and very large. Okay, because again, subtraction sign here, right? All right, delta G will be positive under these conditions. Remember, positive, not spontaneous. So if you have a negative delta H and it's small, delta S is negative. I'm sorry, the delta H is small and negative, and the delta S is negative and large. Or also very high temperatures, because of this relationship here. The larger that T, the bigger the number is going to get. When delta H is positive and delta S is positive and small, or very low temperatures. And then when delta H is positive and delta S is negative, and that is never spontaneous at any temperature, no matter what you do. Now, this is an important part. When delta G equals 0, the reaction is at equilibrium. So let's talk about this in terms of Q versus K. When we talked about K in relation to equilibrium, what we said was, if K was very, very large, the product side was going to be favored. If K was very, very, very small, the reactant side was going to be favored. Now we're going to look at it in terms of spontaneity, what's going to happen, and comparing Q to K. Q mathematically is solved the exact same way as K, products over reactants. However, Q is at any given point in the process of a reaction, where K is specifically at equilibrium. So when Q is less than K, equilibrium has not been reached yet, and it will favor going towards the product side. If Q is greater than K, then equilibrium has been passed, and we're going to come back to forming more reactants to get back to an equilibrium. When Q is equal to K, we're at equilibrium. So this little chart here is your new lifeline. Print this out, write it down, copy it, something, okay? This is telling you what is going to happen at low and high temperatures depending on the sign of my H and my S, okay? So for example, if I have a negative H and a positive S, then at low temperatures, it'll be spontaneous, and at high temperatures, it'll be spontaneous. Remember they just said a few minutes ago that, when I have the negative and the positive, that's most favorable, okay? If I have a positive H and a negative S, it's going to be non-spontaneous at low temperatures and non-spontaneous at high temperatures. All right. If I have a negative and a negative, spontaneous at low temperatures, non-spontaneous at high temperatures. Why? Because the bigger this T gets, remember, negative and a negative, right? So that's really going to be positive. The larger that T, the larger that whole term becomes. It'll be positive because it's minus a negative, and mathematically it'll override the negativeness of the delta H. And then of course, positive and positive, it's non-spontaneous at low temperatures and spontaneous at high temperatures. This was kind of the reverse of our ice equation. So if you can think about it in terms of liquid and gas, at lower temperatures, I'm not going to have steam. At higher temperatures, I will though. So here's just an example of calculating using Gibbs free energy. So what you're given here is a reaction. You are both given the delta H and the delta S's. Now, sometimes you will have to calculate the delta S and the delta H. Sometimes it'll be given to you. You're never expected to memorize what they are. You're either going to have to solve for one or it's going to be given to you like in this example. So the first thing it asks you to do is calculate delta G at 25 degrees Celsius and determine if it's going to be spontaneous. Now, before we determine if it's going to be spontaneous, let's just look at what's happening here. I got a gas, and the gas is going to a solid and a gas. So I have different things, and I'm getting less organized because the gas is part of it is going to a solid. But then I also still got a gas out there. And of course, my moles are going from 1 to 3. So this could maybe go either way. Let's see what happens and if the temperature makes a difference. So we're going to use our equation. Okay, so we're going to use our equation, this one right here, and we're literally just going to plug and chug. Remember that 25 degrees Celsius, we got to convert to Kelvin. And remember, always pay attention to the units. Note that this is in kilojoules, but delta S is in joules. So we're going to have to convert one of them. It's always better to convert the kilojoules first and then plug and chug. So this 95.7 has been converted to joules, plugging in the temperature and the delta S, and we're getting a positive 53.3 times 10 to the 3 joules. So this is a positive delta G, and therefore not spontaneous. Now, I could ask you, at what point does it become spontaneous? That's part B. If the reaction is not spontaneous at 25 degrees Celsius, determine at what temperature, if any, the reaction becomes spontaneous. This is where you're going to set delta G to 0 and then solve for a new temperature. So we're still using our same numbers from our delta H and delta S. We're going to set delta G equal to 0, and we're going to solve for T. So at 673 degrees, 673 Kelvin, that reaction will become spontaneous. So compared to our 298 Kelvin, that's a really, really high temperature. And if you remember, we have here a positive delta H and delta S. If we go back to our chart, positive and positive, it's going to be spontaneous at very high temperatures. Go ahead and practice this one on your own. And if it is not spontaneous, I want you to determine at what temperature it is spontaneous. That's it for part 1 of Chapter 18, Thermodynamics.